Hey, this is Charlie Thompson, and this is the lecture video for Chapter 2, Energy in the Atmosphere. Let me pick up the little lasery pointer thing. Hey, there you go. Cool. This is Death Valley. I chose Death Valley because it's hot. Here's the topics for the modules. I'm going to ignore those and say, here's what we're going to talk about. How does energy flow? How does energy move around? I mean, it comes from the sun, comes into Earth, but it doesn't just sit where it lands. So how does energy actually move around? Where does energy go? So now we're talking about spatial patterns of energy flow. We'll talk about what controls Earth's temperatures. Why are some places hot? Why are some places cold? That's annual average temperature. And then why do some places have no difference between summer and winter? And other places have huge differences between summer and winter. And that's temperature range. So what are temperatures? Earth's temperature patterns. So we'll talk about what creates those patterns and then what those patterns are. So let's jump in. Energy balance. So energy from the sun enters the atmosphere, warms the surface, evaporates water, creates weather, and then goes back out into space. That's the short version. There's a great diagram. We get shortwave, light, and infrared, and a little bit of UV. 31% bounces out to space. Half of the energy that's left makes it to the surface. Some of it warms the atmosphere, some of it warms the surface, bounces back and forth. That's the greenhouse effect. And then it all goes back out to space, except a little tiny bit, because we've added gas to the atmosphere that holds on to heat. That would be carbon dioxide. So energy is the capacity to do work or move material. When we're talking about temperature, that's actually energy of motion. This goes back to the discussion of the thermosphere, the upper layer of the atmosphere by temperature, that there is high temperature, so the molecules there are really excited, but there's no heat. So temperature is a measurement of kinetic energy, the energy produced by the molecular vibrations that we measure as temperature. There's potential energy, that's stored energy that has capacity to do work. A mousetrap that has been set has potential energy. A gasoline, dam reservoir, energy and heat. Heat is the flow of kinetic energy between molecules. So if there's no molecules, there's no heat. Or rather, if you just had the one molecule, there wouldn't be any heat. It doesn't matter how excited that molecule is. If there's nothing for it to share it with, if that energy can't flow, there's no heat. Heat flows from hot to cold. Two very important kinds of heat. Number one is sensible heat. That's the heat that we sense. That's why it's called sensible heat. If you feel it, that's sensible heat. And then there's latent heat, and that's energy involved with a change of state of water. So we'll talk about this later, but water is a really amazing substance, and it takes an enormous amount of energy to change the state. To evaporate water, lots of energy involved. When water is condensed, when it condenses from a gas to a liquid, it releases heat. When it freezes, it releases heat, an enormous amount of heat. When it melts, it absorbs heat. When it evaporates, it absorbs heat. So it doesn't change the temperature, it just changes the state, and that's called latent heat. So these are four ways that heat moves around. And as you're studying these, I would try to keep track of what's moving. Is it the energy is just moving, or is the energy and the molecules, are they both moving? So with radiation, it's just the heat traveling through space. No molecules required. The energy is just traveling through space. As opposed to conduction. So conduction would be like you pick up a pan and the handle is hot because the pan is on the stove. The energy is flowing from molecule to molecule to molecule. So the molecules themselves aren't moving, but the energy is flowing from molecule to molecule. With convection, the molecules absorb heat and then go someplace else and give the heat up there. So this is the way a refrigerator works. A refrigerator just moves the heat from the inside of the refrigerator to the outside of the refrigerator. It's the way we warm and cool our homes. And with convection, both the energy and the molecules are moving. So with radiation, just the energy is moving. There's no molecules required. like sunlight coming to Earth from space, that's radiation. With conduction, the energy is moving, but not the molecules. But there are molecules. And with convection, not only are they molecules, but the molecules absorb the heat and then they move someplace else. So that's radiation, conduction, and convection. Latent heat is the energy absorbed when liquid water evaporates. It's the energy released when water vapor condenses. And it takes an enormous amount of water, an enormous amount of energy to evaporate water. We'll talk about that later. But latent heat is huge. It's a huge mechanism of heat transfer from the tropics to the poles. So here's just the words. You can read those on your own. Shortwave and long-wave radiation. So shortwave is light, long-wave is heat. Shortwave comes from the sun. Long-wave is what Earth radiates. The sun also does radiate some long-wave, but it's mainly shortwave. So these two graphics are showing outgoing light. So this is light bouncing off of Earth. That's called albedo. We'll talk about that in a minute. Albedo, how reflective something is. And this is heat going out. So I think it's interesting that there's a couple regions that have very high outgoing light. So like the clouds of the Amazon, the snow-covered Tibetan Plateau, the clouds across the world's tropical rainforests are really good at reflecting light. Also the Sahara, really good because it's just sand. There's no vegetation, there's no clouds. So the light-colored surfaces are reflecting light. Middle of the ocean, not a lot of clouds there, and so not a lot of reflectivity. But for heat, the places that have low reflectivity, because there's low clouds, those act like windows for the heat to go out. So really high heat values going out to space in the areas that have low reflectivity, except the Sahara. So the Sahara during the day bounces light out, and at night it's bleeding heat because there's no clouds to absorb the heat. So insolation is sunlight and albedo. How does light move? Number one, transmission. Kind of like radiation, just light going through space. Passage of shortwave or longwave through either the atmosphere or water. This would be sun coming into Earth from sunlight coming into Earth, this transmission. If we look at this, this is the pattern of insolation. This is energy received at the surface now, received at the surface over the course of a year. And the highest values are in the tropics or the subtropics, right where the world's deserts are. Air is sinking in the atmosphere. As it sinks, it gets compressed, it gets heated up, the clouds go away, so cloudless skies. So there's clear skies, so there's very low latent heat, very high sensible heat. Also, like if you were to ask me before I was a geographer, hey, what latitude gets the most energy over the course of a year? I would have said, well, duh, the equator, because it's in the middle. The poles get the least, the equator gets the most, right? No. The sun is parked for a couple of months over the Tropic of Cancer, and then it migrates to the Tropic of Capricorn, where it stays parked for 3 months, and then it, for 3 months, moves back up, parked over the Tropic of Cancer for 3 months, moves for 3 months, parked for 3 months. So the highest values aren't found at the equator, but found at the tropics as a result of cloud-free skies, as a result of low latent heat, and also the analemma. If you remember the path of the sun, that the sun, like I keep saying, it's parked for about 3 months over the Tropic of Capricorn, moves up for 3 months, it's parked over the Tropic of Cancer for 3 months, then for 3 months it moves back down. So the sun spends about 3 months of the year parked directly over each of the tropics. 3 months here, moves up for 3 months, 3 months here, moves back for 3 months. So the region on Earth that gets the most concentrated energy from the sun is smack dab in the tropics, subtropics, for those two reasons. Scattering. Scattering is when light gets bounced in all directions, like off of a mirror ball. That's my favorite example of scattering, would be a disco ball, because the light comes in one way, but it goes out every possible way. There's two types of scattering you need to know. There's Rayleigh scattering, which makes the sky blue because small gas molecules scatter blue light first. So the sky is blue because it reflects blue, because the size of the molecules are just right to reflect mostly blue. And that's called Rayleigh scattering. There's also Mie scattering, named after the scientist that discovered it. Mie scattering happens off of very large particles, dust, smoke, soot, ash. And because all frequencies scatter equally, that makes the sky look whitish. Big particles of dust and smoke reflect all wavelengths, so the sky looks whitish. Refraction also accounts not only for the blue color of the sky, it's also what causes rainbows as the light gets bent inside water droplets and comes out at a different angle depending on its wavelength, which is a function of its color. So different colors of light get refracted in different directions off of water droplets, making beautiful rainbows. Refraction is when light gets bent. It gives us 8 extra minutes of daylight. It gives us rainbows, and it gives us mirages. So when light passes through space and hits Earth's atmosphere, the light changes direction. So it gives us 8 minutes of daylight. It gives us mirages. Reflection, the term for reflection is albedo. Albedo is the percentage that's reflected. If something reflected all the energy, the albedo would be 100%. Lighter surfaces reflect more, darker surfaces absorb more. So this would be a high albedo surface, this would be a low albedo surface, which would make sense because plants absorb sunlight, so you'd expect that they're trying to eat all the sunlight they can. What? Albedo. So, a couple albedo numbers for you to know. Earth's average, 31%. Almost a third of the energy coming in from the sun gets bounced right back out to space. The moon. The moon is really not that bright. I mean, you can read a newspaper on a full moon because it's really bright, but it's only reflecting about 7% of the energy. So the moon reflects as much energy as asphalt. Never would have guessed that because it's so bright. So if you were able to see Earth and the moon, if you were in space, and you're in space at a position where the moon and the Earth were the same size, so you'd have to be like way closer to the moon, farther away from the Earth. But if they were the same size, Earth would be 4 times brighter than the moon. Snow, water is really, really, really good at reflecting light. This is incredibly important. We talked about the idea of the ice albedo loop in feedback loops, that as Earth warms, you lose ice. So this is why. Fresh snow can reflect 95% of the sunlight right back out. So if you have snow, but then you're revealing dark-colored rock instead of reflecting 95% of the light, boom, now you're absorbing 95% of the energy. So a huge transition as snow and ice melts. So ice in the ocean, as it melts, reveals water, which has lower albedo. Ice on the land, when it melts, reveals dark ground that absorbs heat. What else happens to heat energy absorption? Or rather, what can happen to light? Molecules absorb the energy from the light and get warm. Sun shines on the ground, ground gets warm. That's actually absorption. That's it for albedo and insolation input. Let's talk about the greenhouse effect, clouds, and atmospheric warming. So greenhouse gases absorb and emit radiant energy. The Earth emits long-wave energy, and that long-wave heat energy gets absorbed by water vapor, carbon dioxide, and methane. Those are 3 very powerful greenhouse gases. There is no greenhouse effect. The atmosphere acts like a blanket. It really should be called the blanket effect. A greenhouse actually traps heat. A blanket just slows down the passage of heat. So what's happened is we've added blankets to the atmosphere that are trapping the heat. The heat is leaving slowly, but it's just as if you have a fever and someone comes in and keeps putting blankets on your bed. The more blankets they put on, the warmer you're going to be because heat is still traveling from your body through the blankets to your room. But the more blankets we have, or the more blankets you have, the hotter you're going to be. The more carbon dioxide in the atmosphere, that thicker the blanket is, the more heat it's going to hold on to before it releases it to space. It's not a greenhouse. It's not a greenhouse. It's not a greenhouse. Clouds are incredibly important in the energy balance. Low, thick clouds act to cool Earth because they reflect the light, so it never comes in and becomes heat. High, thin clouds warm the lower atmosphere because the light comes in, which becomes heat, and then that heat gets trapped by the clouds. So low, thick clouds reflect the light, so it never becomes heat, so it's cooler. High, wispy ice crystal clouds let the light in, which becomes heat, and then they trap that heat. After September 11th, we were able to do studies and track how much cloud cover there was, how much energy was coming in from the sun, and what the temperatures were. And scientists were able to quantify, like put numbers on how much global warming is caused by clouds from airplanes. Clouds, cloud types, high clouds let in light, trap the heat. Low clouds reflect the light, making it cooler. That's saying just the same thing. High clouds, jet contrails, chemtrails aren't a thing. Contrails are. They're condensation trails. Jet fuel is a hydrocarbon, so the molecules that make up hydrocarbons have water. So when hydrocarbons are burned, when jet fuel is burned, the chemicals that result are water vapor and carbon dioxide. The water vapor becomes ice crystals and makes these high clouds. Aerosols. So when you use aerosols, mean little particles in the atmosphere. Global dimming refers to the idea that Earth is cooler by about half a degree because of air pollution. The air pollution on Earth, it's killing over 10,000 people a year, at least, from just poor air quality. But the air pollution on Earth is actually it increased the albedo. So if you increase the albedo, the energy gets reflected out as light and it doesn't become heat. So Earth is about half a degree cooler because of air pollution than it would be without that air pollution. Typically, after a volcanic eruption, the temperature drops for a couple of years because of the increase in albedo. 1991 eruption of Mount Pinatubo is one of the most famous because it was a massive eruption. The ash went global, and we had more beautiful sunsets for a couple of years. In fact, you can Google photographers. There's like a couple photographers who made their career out of selling sunset photography done during this period, Pinatubo lighting. So if you Google like Pinatubo sunsets, you'll find these people who are selling these photographs taken when we had prettier sunsets because the particles in the atmosphere were reflecting the light differently. So they increased the albedo, so less light was coming in, but then also at sunset, they scattered the light, so the colors at sunset were richer. That's it for the greenhouse effect, clouds, atmospheric warming. Let's talk about the Earth-atmosphere energy balance. So there's a distribution of energy by latitude. This is review. The tropics have an energy surplus. They gain more energy than they lose. The poles, they don't get a lot of energy because of low sun angles, high albedo off of ice, and the fact that they have often 6 months of darkness. So not a whole lot of energy getting to the poles, lots of energy going to the tropics. So the tropics are gaining more energy than goes out from the tropics because that heat goes to the poles, which is why the poles are able to lose more energy than they're gaining. Around 36 degrees north and south, it's a balance. So the poles are an area of energy surplus. The tropics, I do that every time. The tropics are an area of energy surplus. The poles are an area of energy deficit. About 36 degrees north, the amount of energy going in and going out is exactly the same. This is, again, part of the reason the tropics are hot and the poles are cold. Oh, yeah. So here is a diagram with a whole bunch of numbers. I will go through it step by step and let you know all of the numbers that you need to memorize. In fact, yeah, I was going to say, with YouTube, if you hit the back key on my computer, it backs up 5 seconds. You're probably going to want to go through this a couple times. Pause it. I would draw out the sketch, actually. So if I was watching this at home at this point, I would pause it. I would draw out the sketch and have the arrow coming in from the sun and one going out to space, arrow coming in from the sun going to the atmosphere, arrow from the sun going from the surface. I would then have one arrow going from the surface to space, one going from the surface to the atmosphere, and then I would have one arrow going up from the surface to the atmosphere and a big arrow going down from the atmosphere to the surface. So those are the arrows that I would draw. And we'll start out with, and the whole point of this is to study where energy goes. So we know exactly how much energy we get in from the sun every day, and now we're going to find out what that energy actually does. So it's like an accounting of the energy. So we know how much energy came in, and we know how much went out, but what happened in between? Where did the energy go? What did it do? So right off the bat, 31%, boom, gets blocked. The bouncer says, you're not on the guest list. Earth's albedo, 31%. The surface reflects 3%. The atmosphere, gas, dust, clouds reflects 28%. I wouldn't have guessed that. I would have thought that the surface would have reflected way more energy, but it doesn't. So total albedo, 31%, which leaves us with 69%. Ozone is going to absorb another 3, so now we've got 66% left over. So 21% is going to warm the atmosphere, and about 45% is going to warm the surface. So 45, 21 is 66, and 3 is 69, plus 31 is 100. So that's 100 units of energy coming in. Of the energy going out, 23% goes from the surface to the atmosphere and then right back out. And that's weather. It says latent heat and convection. What that really means is this is energy used to evaporate water and then to move it around through ocean currents and air currents. So this is weather, a quarter, 23%, almost a quarter of all the energy we get from the sun just makes weather. That's an incredibly important number. You need to know that. So we had 45 units at the surface. We just lost 23, which leaves us with 22. So we've got 22 units of energy at the surface. 8 is going to skip the atmosphere, miss me with that. Boom, yeet, out to space. Bye. I'm going to skip the atmosphere. I ain't warming that up. I've had enough of this planet. I'm back out. So that leaves us with 14%. So constantly, 110 units are going up at the same time 96 is coming down. This is the greenhouse effect. This is the blanket effect. Energy is flowing back and forth. Amazing amounts of energy. Way more energy than is actually coming in on any one day is going back and forth from the surface to the atmosphere and the atmosphere to the surface. So we can break it down and study where the flows are. 110 units coming up. At the same time, 96 units are coming back down. So that's to help you grasp how much energy is moving around, and the answer is more than is coming in every day. But the net is only 14. We're losing 110, we're getting 96, so the net is 14. And that accounts for all the energy at the surface, right? We had 45, we lost 23, which left us with 22. We used up 8, which leaves us with 14. Except that you also need to know that that 14 involves 110 units going up at the same time 96 is going back down. I think of this as if I gave you $110 and at the exact same moment you gave me $96. What is that? $206 was the total amount of money that was exchanged, but the net is the same as if I gave you $14. So the net effect is 14 units from the surface to the atmosphere. But what's really happening is enormous amounts of energy flowing back and forth in both directions at the same time. So the numbers that you need to know, actually all of these, you need to know all these numbers for the test. 100 units in, albedo is 31%, ozone absorbs 3, the atmosphere absorbs 21, the surface absorbs 45. That all adds up to 100. Then we've got our 14 and 23 and 8. That's 66, plus 3 from the ozone is 69, plus the albedo of 31 is 100 units back out. Whew! That's it for the Earth-atmosphere energy balance. Let's look at the energy balance at Earth's surface. So typically, these are a bunch of words. Typically, the warmest time of day is the afternoon. The most energy directly in from the sun happens at at noon. But typically about 3, 4 o'clock is when the warmest time of day is. And that's because at that time, we're still getting energy from the sun, but also the surface is now emitting energy. So all day long, the surface is absorbing energy and then it starts releasing that energy. So at the warmest time of day, the surface is releasing energy, the atmosphere is releasing energy, and we're still getting energy in from the sun. So over the course of a day, the coldest time is just after sunrise, because it takes a while for the surface to warm up. The warmest time is 3, 4 hours after solar noon, because by then we're still getting energy from the sun, but the surface and the atmosphere are releasing heat. So on a daily basis, this is what it looks like. On a monthly basis, it would also look the same. Like if this was the December solstice, and if this was the summer solstice, the warmest month is often a month after the summer solstice, and the coldest month is often a month after the winter solstice, because it takes a while for Earth to warm back up, and it takes Earth a while to start cooling off. So there's also a seasonal lag, that the time of year with the least energy and the most energy, the coldest month is like a month after, and the warmest month is like a month after. This is talking about energy at the surface, and there's only a couple different things that happens to energy. Net radiation is the idea that incoming shortwave minus outgoing shortwave plus incoming long wave minus outgoing long wave equals net radiation. So we've got shortwave coming in as light, going out as albedo, heat coming in, heat going out. We also have, and I'm surprised I didn't have this, latent heat. There's also latent heat into this equation. So let's talk about that. Net radiation flows from the surface through 3 pathways. So if there's heat at the surface, you're either going to have sensible heat, it's going to make it feel hot, or you're going to have latent heat. Latent heat of evaporation, the only 2 things that happen with heat energy at the surface, really. Sensible heat, it makes it feel hot, or if there's water, the energy is going to get absorbed in evaporating the water. So those are the only 2 things that happen with heat energy at the surface, and that's incredibly useful. The third thing is ground heating and cooling, where it flows in and out of the surface, which is just the transfer of sensible heat. I don't really see it being different. So I'm just going to go back and say, really, you got your sensible heat, and you got your latent heat. That's pretty much it. If there's heat energy at the surface, it's going to evaporate water. If there's no water, it's just going to make it feel hot. So these are 2 images of the same place. This is the Imperial Valley. It's down in Southern California, right on the US-Mexican border. This is an image that was produced using a GIS. So using layers of information, they were calculating, or rather displaying, how much water evaporates in centimeters. So 100 centimeters is about 3 feet. So 1 meter, you're looking at 1 foot. 180 centimeters, about 6 feet of water evaporating over the course of a year. So off the surface of the Salton Sea and these dark blue field areas, they're losing 2 feet of water. Out here in the unirrigated desert, the actual amount of water evaporating is less than an inch. So looking at the vegetation seems entirely plausible. But I wanted to talk about how they actually calculate this. So if I back up the page, there's only 2 pathways. It's either sensible heat or latent heat. So using satellites, they know how much energy came in from the sun. Using satellites, they know what the temperature was. So if you know how much energy came in, and you know how much energy made it feel hot, you've solved for everything except latent heat. The missing amount of energy is the energy that was used to evaporate water. So by solving for the missing energy, they can calculate exactly how much water actually evaporated. So the company that did this, David's Engineering, they're a company in Davis. They do irrigation consulting for large water districts. So if you were the Imperial Irrigation District, you would want to know, what's the worst case scenario? Hottest day of the year, how much water total are we going to need to have to be able to deliver to all of our farmers on that day? So calculating what the maximum evaporation would be, they use the hottest day of the year, They studied how much energy came in. So let's say there was 100 units of energy, 100 watts came in, 50 watts made it feel hot. The missing 50 watts evaporated water. So 500, over 500 watts per gram to evaporate water. An enormous amount of energy. We'll talk about that later. But the latent heat of evaporation is absolutely enormous. And by knowing how much heat was used to make it feel hot, by knowing how much energy came in, you can solve for the missing heat and figure out what the actual evapotranspiration was for that day. Yeah, I just backed it up because I wanted to say that's a great test question. How could you solve for latent heat to calculate actual evapotranspiration? So let's talk about temperature concepts and measurements. Temperature is the measurement of kinetic energy. There's 3 temperature scales. There's Fahrenheit, there's Celsius, and there's Kelvin. That's interesting because all 3, well, 2 of the 3 are names. Fahrenheit was Daniel Gabriel Fahrenheit. He was a German scientist who was studying temperature. Anders Celsius was a Swedish scientist, and Lord Kelvin was a British scientist who was also studying temperature, although Kelvin wasn't his name. So the 3 different, and I should point out again, we are the only country except for Myanmar and Liberia that uses Fahrenheit. The rest of the world uses Celsius, which is a way better system. Water freezes at 0, boils at 100. In between, there's 100 Celsius degrees, as opposed to our system, Fahrenheit. Anybody ever wonder what 0 is? Like, what the hell happens if water freezes at 32? I would think that would be pretty special. Like, that's what Celsius used. Water. Let's use the melting point of ice, set that as 0. Boiling point of water, we'll call that 100. We'll divide everything else up into 100 degrees. So 0 Fahrenheit was as cold as Fahrenheit could get a mix of crushed ice and salt. He was making like virgin daiquiris and trying to get this mixture of salt and crushed ice and water as cold as he could get it before it froze, trying to duplicate conditions, for example, in the ocean. So 0 Fahrenheit, probably close to the freezing temperature of the ocean, although I think the ocean actually freezes lower than that. So 0, doesn't mean anything. 100, that's nothing special. 212, that's where it boils. And the Kelvin scale, the degrees are spaced as far apart as the Celsius. So it's like 1.8 Fahrenheit degrees equals 1 Celsius degree, and 1 Kelvin equals 1 Celsius degree. Kelvin is both singular and plural. That's a weird word. So you don't have kelvins. There's never anything kelvins. It's always Kelvin. 373 is 100, 273 is 0, so there's an offset of 273 degrees between 0 Celsius and Kelvin. Kelvin is based on the idea that temperature is a measurement of the kinetic energy. And so if there's no energy, there's no movement. So 0 Kelvin is absolute 0. At absolute 0, there is no energy for any movement, so there is no movement. So absolute 0 is 273 degrees Celsius, 273 Celsius below 0 is absolute 0. That is the temperature at which all molecular motion ceases. When we measure temperature, it's always measured outdoors in a small shelter with high albedo and good ventilation. This is somebody measuring temperatures. There's the temperature sensor. You can see it's ventilated, so heat doesn't build up. It's white, so it doesn't absorb heat. It's a high albedo ventilated structure. What else do they have? Some sort of optical sensor. I don't know what that's about. Maybe fog. Wind vane telling wind speed and direction. They've got a solar panel, probably just to run the batteries. Skin temperatures. So now this is annual average surface temperature, and it's a predictable pattern. Right here in the subtropics, right here in the subtropics, highest temperatures. Subtropics, subtropics, hotter than the tropics. So the regions of the world that have the highest temperatures are in the subtropics because they have clear skies and the sun parked sitting right here for 3 months on bake. 3 months moves, 3 months on bake. This is where the world's deserts are. The American Southwest and the Mexican Southwest, the Sahara, Saudi Arabia, parts of India, Pakistan, Afghanistan, Australia, the Skeleton Coast of Namibia, the Kalahari Desert, and then the Atacama Desert, which is the driest desert in the world. Surface temperatures way hotter than air temperatures. You can fry an egg on the ground, and you wouldn't be able to fry an egg in the air. And the overall pattern, I love this map because if you zoom in, you can see the details, and the overall patterns are immediately obvious for average temperature. Latitude is the most important, going from low to high to low. So it's latitude followed by elevation. So you can see the Rockies in here. Red doesn't work, does it? You can see the Andes a little bit. The Ethiopian highlands right there. You can see the Sierra Nevada. If you had a different image, you could zoom in and see the cooler areas of the Appalachian Mountains. You'd see the cooler areas of the Alps, the cooler areas of the Scandinavian mountains. And the top of the Greenland ice sheet is like 10,000 feet above sea level. So it's cool to be high. Yeah, I would just write that down. Remember, kids, it's cool to be high. So high elevations are cool. High latitudes are cool. And again, looking at insolation input, you can see that the pattern of insolation input is a major driver of the patterns of skin temperature. Measuring temperature, we're going to look at average annual. So that's every month added up, divided by 12. And then the annual temperature range is the difference between the hottest and the coldest months. So average is all the months added up, divided by 12. And then temperature range is the difference between the hottest and the coldest monthly temperatures. Latitude is the most important factor of temperature, both average and temperature range. Oh, it just occurred to me, I should have the average temperatures here too. So you can see, right, 13 degrees south in Brazil, this red line is their temperature profile. So at low latitude at the equator, low latitude has a low temperature range, but high temperature. Looks like it's 80 degrees all year long. High latitude has a high temperature range. You can see the peakiness, how peaky it is, how much of a peak there is. Like there's no peak, more of a peak, really good peak. So high latitude has a high range, but low average temperature. Like if the average, probably around 0 Fahrenheit. Oof. So as you move away from the equator, the temperature goes down, but the temperature range increases. New Orleans, Louisiana has a much bigger temperature range than Brazil. The average temperature is also lower. It looks like the average temperature is around 70 instead of 80. In Quebec at 45 degrees north, so this would be like up Oregon, Washington. Looks like the average temperature is around 45. And an annual difference between 12 degrees and 72 degrees, so like a 60 degree range. Couple degrees, 60 degrees. So latitude is the most important factor for average temperature and temperature range. Ooh, land water heating differences. This is huge for range. Land water heating differences affect temperature range. Water heats and cools very slowly, and there's a bunch of different reasons for this. Definition of calories. 1 calorie changes the temperature of 1 gram of water by 1 Celsius degree. So the actual definition of a calorie involves 1 gram of water. 1 calorie is the amount of heat energy required to change the temperature of 1 gram of water by 1 Celsius degree. 1 gram of water has a volume of exactly 1 cubic centimeter, which is about a sugar cube. Specific heat is the number of calories required to change the temperature of 1 gram of a substance by 1 Celsius degree. So the specific heat of water is 1. 1 calorie changes the temperature by 1 degree. So that's the definition of a calorie. The specific heat of rock or sand is a 1/4 calorie. So if you put 1 calorie into water, into a gram of water, and you put a calorie into a gram of rock, the water is going to heat up by 1 degree. The rock is going to heat up by 4 degrees. So this is something that you all know. I'll talk about it in just a second, but if you've ever been to the beach, you know exactly what I'm talking about. So, and that is that when you go to the beach first thing in the morning, the sand is cool and the water is cool, but then in the afternoon, the water is still cool, at least if you're in California, but the sand is broiling hot. That's because part of that is the difference in specific heat. That same amount of energy for the same amount of weight of rock or water, the rock is going to heat up 4 times as much. So here are the land-water heating differences, and they're all of them just get lumped into the category of continentality. So places inland have lots of land, so they have a big range. Places on the coast have a small range because the water doesn't change temperature a whole lot. And let's go through the reasons. Number 1, evaporation. Every gram of water that evaporates, it just took 540 calories of heat away from the water. As it evaporates, the water vapor leaves the water, and that water vapor is taking with it 540 calories. That's the latent heat of evaporation, is 540 calories. Every gram of water that evaporates takes 540 calories of heat with it. So the water that's left behind is now cooler. In fact, that's going to be a feedback loop. That's going to be a negative feedback loop. The more, as you heat water, it evaporates, but as it evaporates, it cools itself. Number 2, that land, when light shines on some of these are obvious. Like land is opaque, right? When sun shines on the ground, just the top heats up, but water is transparent. So in clear conditions, the top couple hundred feet are going to be absorbing heat instead of just the top millimeter absorbing heat. Land has a lower specific heat, around 1/4 calorie. Water has a specific heat of 1. Land doesn't mix. You're never going to drive by a field in the afternoon and see it like bubbling and boiling. That's the land so the top layer gets hot, and then by conduction, it'll get transmitted. But water is going to move by convection. So the water gets hot, and then it goes someplace else. And now cold water is left to replace it, and it has to absorb heat. All of these factors, evaporation, transparency, higher specific heat, and mobility, contribute to this idea of continentality. And these are just words describing each of those: specific heat, movement. Marine climates, maritime climates have moderate temperatures. If you like mnemonic devices, like everything's alliteration, marine climates are moderate. Continental climates in the middle of a continent have a huge temperature range compared to the coast. Let's look at examples. San Francisco, Wichita, Kansas. San Francisco has an average temp of 14.6, Wichita an average temp of 13.7, but San Francisco is going from like 50 to 65, so a 15 Fahrenheit degree range, as opposed to going from 30 degrees to 80 degrees. They have a 50 degree range in Wichita because of those land-water heating differences. They're both at the same latitude, 37 degrees, but a 15 degree range, a 50 degree range because of those factors: specific heat, evaporation, transparency, and mobility. The factors that cause continental climates or maritime climates. It's always nicer by the coast because the water doesn't really change temperature. Altitude and elevation are 2 terms that are similar but different. Altitude is your height above Earth's surface. Elevation is your height above sea level. For our class, this doesn't matter, but some of the people that use the textbook are pilots in training, and the difference between altitude and elevation is huge. Like you could have positive elevation, but a negative altitude, which would mean that you've crashed and the airplane is now below the surface of Earth. But you're still above sea level because you crashed into a mountain. Cool off as you climb. If you go to the mountains, it's cooler. So high elevations have lower temperatures. High altitudes have lower temperatures. Clouds moderate. They don't really make it hotter or colder. They just moderate temperatures. So, not really Clouds are very important. In understanding clouds is important to understanding Earth's energy balance and energy budget and how energy flows around Earth. As a temperature control, it makes the daily maximums lower and the nightly minimums higher. So it acts to moderate temperature. So you'd still have the same average temperature, right? So cloud cover just moderates temperature for the most part. Ocean currents. Warm currents off the east coast, cold current off the west coast. So if you're on the west coast, you probably have dry summers. If you're off the east coast, you probably have humid, rainy summers because of the warm current off the east coast. Warm currents evaporate more easily, like the Gulf Stream, so you get lots of hurricanes, lots of thunderstorms. The Gulf Stream, incredibly warm, bringing heat up the east coast of the United States over to Europe. You can see, I think we've looked at this in the Null School. Ooh, I need to put that video up. So in the Null School video, you can play around with sea surface temperatures and realize on the same day off of San Francisco, the temperature is going to be in the 60s. And at the same latitude on the same day off the East Coast, the water temperature is going to be in the 80s because the oceans rotate clockwise. So there's a warm current going up and a cold current coming down. Here we have another west coast, so there's a cold current coming up and a warm current going down, cold current coming up, warm current going down, warm current going up off of Asia, and then cold current coming down the U.S. west coast, making deserts and Mediterranean climates, cold current coming up, deserts, Mediterranean climates, desert, Mediterranean climates, deserts, Mediterranean climates. So climates are going to be a function of latitude, continentality, water temperature of the ocean currents offshore. Oh, we're up to the urban environment. Those are microclimates. Micro, small climate. That just means a small area. The urban heat island effect. Cities are hot. Rural areas, suburban areas are cooler because there's more vegetation. Let's look at a picture. Typically, the highest values are downtown. The lowest values are going to be places with lots of vegetation. Oh, right? Because of, backing this up, we could look at the picture of the Imperial Irrigation District study again. The more water there is to evaporate, the more heat energy gets used up in latent heat, the less heat energy is available for sensible heat. So some places like Miami, they've got high values for both. Some places like Arizona, they just have very high heat values, very high sensible heat, very, very low latent heat. And then some places would have higher latent heat values and then lower. So at the same latitude, you could find a place by the coast that would have more water vapor or more water to evaporate. They would have lower sensible heat. Lower sensible heat, more latent heat. No latent heat, higher sensible heat. So the cities are often 2 to 5 degrees warmer than the surrounding countryside because there's less evaporation. So some of the things to mitigate the urban heat island, you can plant more trees. The more trees you plant, the lower sensible heat is. They're going to absorb heat and convert it into latent heat. SMUD will come and install a shade tree for you. One big shade tree does as much to cool your house as a window-mounted air conditioner. And in fact, parking lots. In California, there's a law that for every so many square feet of parking lot, you have to have so many square feet of tree canopy, but virtually nobody is in compliance. So instead, we have black asphalt parking lots soaking up heat. High albedo rooftops. Different roof materials would make our houses cooler. Lighter pavements would make our cities cooler. So NASA wanted to study this and put numbers on it. So they flew over Memphis and they flew over Sacramento, which is great because you live in Sacramento, right? So we can look at this and figure out patterns of high latent heat and patterns of high sensible heat. So right here, we've got the rail yard. It's just dirt and metal, so no evaporation. And that indeed is one of the hotter places in Sacramento. Lower places that are cooler in temperature would be like Capitol Park, which looks dark, right? So for visible, the albedo is low, but there's all this latent heat from the vegetation. I think this is down by the Crocker. So latent heat from water evaporating. In fact, there's a good correlation between tree cover and temperature. Where I live in Davis, there's in fact an entire subdivision, and the builder deliberately narrowed the streets so that the trees would shade them to make it cooler. That's Village Homes out in West Davis, and they're actually world famous for an ecologically designed development, and that's part of it, is deliberately narrow streets. Right, like you can look at the freeways, and the freeways are just soaking up heat. The streets are soaking up heat. The river's cold. And then the areas with lots of parks have lower temperatures. It's the same thing. This is just New York, same study. Regular roof was hitting almost 80 Celsius, but a white colored roof was registering way lower temperatures. And then a green roof, or a living roof, was the lowest of all. So a green roof, I stole this from the internet, so it could be Norway, could be Lake Tahoe, I don't know. But all the plants are going to absorb heat. They're going to absorb light, and they're going to make it into plant food rather than heat. Now I love this one. I have no idea what this is. It looks like they store landscaping equipment, but that's gorgeous. I would much rather look at that than a dark colored roof any day. There's temperature patterns. Let's put it all together. So we've got two vocabulary words. Isotherm. Iso means same, therm, heat. So those are lines of equal temperature. And then the thermal equator, I'll just show you. If you start at the poles, it's cold. If you start at the poles, it's cold. If you work your way to the equator where it gets warmer and warmer, cold, warmer, warmer. Where the warmers meet up, we've drawn a line and called it the thermal equator. So the big deal out of this is this is January. So in January, subsolar point is in the southern hemisphere. The northern hemisphere is colder, and there's greater temperature change over the land than over the water. So 27 degrees Celsius, 27 degrees Celsius, negative 42, negative 36. And you can see that the thermal equator in the ocean, kind of close to the equator, thermal equator close to the equator, thermal equator close to the equator. Over the land, it's dipped down a bunch. And you can see these isotherms are bending more in the middle of the continent than they are on the coast, because the middle of the continent is cooling off faster than the coasts. In the wintertime, the middle of the continent, like Wichita, way colder than San Francisco. Same thing over here in Eurasia. The largest landmass, the most cooling, the most continentality. So then in summertime, the subsolar point's going to shift north. The thermal equator shifts north. It's still over the equator, still pretty close to the equator, but instead of South America, now it's over Mexico. Instead of Southern Africa, now it's in the Sahara. Instead of over Australia, now it's over India, Southeast Asia. So the thermal equator moves a whole bunch over the land, not as much over the ocean. This was negative 42, now it's in the 20s. This was negative 30, now it's like 15. But the ocean is still like 27 degrees, 27, 24, 27. So not a whole lot of change over the ocean. Oh, and yeah, you can see here the effect of altitude, that all of these lines are bending way, way north over the Andes because it's high and it's cold. So remember, it's cool to be high. High latitude, high elevation, both of those are cool. So here is average annual temperatures. You can see highest values right in the subtropics, lowest values at the poles. There's no data for the southern hemisphere over Antarctica, but you can see Australia. It looks like it's just latitude. Going across the Midwest of the United States, it looks like it's a function just of latitude. You can see a little bit of the Appalachians. You can see the Colorado Rockies. You can see the Sierras. Oh, you can see the Alps, the European Alps. You can see the Tibetan Plateau. You can see the Ethiopian Highlands. And you can see the Andes, that the Amazon is broiling hot, but in the Andes at the same latitude. In fact, at 26,000 feet on the equator, there are glaciers because they are so high that it's cold enough that it's freezing year-round. So there are glaciers where at the same latitude, at closer to sea level, it's a tropical rainforest. Tropical rainforest, glaciers. Same thing. If we could see better into Papua New Guinea, we would see that there's glaciers, again, pretty close to the equator, because the elevation is so high. So high latitude, high elevation, both of those are areas where it's cold. Temperature ranges. largest ranges at subpolar locations well inland. The southern hemisphere, there's nothing there. So here's the map out of the book. So across the tropics, we're looking at like a 3 to 5 degree range between summer and winter. Oh yeah, I should start giving you geographic pickup lines for those of you that are in the dating circuit. Here's this one. Night is the winter of the tropics. So the difference between noon and dawn in the tropics is way bigger than the difference between summer and winter. The difference between summer and winter is 5 degrees and, 20, 30 degree swing during the day. So every day there's a bigger change than there is during the seasons. 60 degree range, this is the highest temperature range in the world. They actually have in Fahrenheit 183 degrees difference between the average winter low and the summer high. So in the winter, it's getting down to negative 100. In the summer, it's getting up to 83. In fact, this region this summer hit 100 degrees. There are parts of Siberia that this summer hit 100 degrees. So it would be way hotter there because they're so inland than it would be on the coast in places where you'd get more energy from the sun over the course of a year. So the pattern, and you can see northern green, there's lots of green. Green is like 30 to 45. There's nothing in the southern hemisphere that's even close to that. 15 to 20 degrees, 15 to 20 degrees. I think this is a glitch in the data. I remapped it for kicks and giggles myself using a newer data set, and I didn't get that pattern. So here we have Siberia, the highest range, and right here in the tropics, the lowest temperature range. In fact, you can see the concentric effect of continentality and latitude. Again, the concentric effect of continentality, as you move away from the coast, the temperature range goes up and up and up. It's not symmetrical because the prevailing winds are from the west. So by the time air reaches Siberia, it's had to travel across the entire continent. And in the summertime, it's going to get warmer. And in the wintertime, it's going to get cooler. So the largest continent right around the Arctic Circle. So they're getting probably 24 degrees difference, 24 hours difference in daylight between summer and winter. So the combination of high latitude and high continentality. There's water here, but like I said, the prevailing winds are out of the west, so it doesn't matter. Wind chill, heat index, heat waves. So heat waves 3 days in a row above 90 Fahrenheit. Wind chill, the combination of air temperature and wind. If it's windy, it feels cooler. And heat index, the combination of high temperature and humidity. We live in Sacramento. It's really hot in the summer, but it's a dry heat. So this is the wind chill chart. As the wind blows, it gets colder and colder. That's pretty much it. Most of wind chill happens at relatively low wind speeds, like 10 miles an hour. It would feel like 30 degrees Fahrenheit. If it was calm, at 10 miles an hour, it feels like 21. So you might have heard of wind chill, usually like Green Bay Packers game at Lambeau Field with the wind chill, it's negative 1,000,000. Well, that only applies to exposed skin. So if you're really smart, you're completely covered. Wind chill only affects exposed skin because it's the effect of wind on the human body. So if you're wearing a snowmobile suit and a helmet, there'd be no wind chill. This is the heat index chart. This correlates relative humidity with temperature to calculate perceived temperature. This is not, red on red, not really great. So if you were, let's just say Arizona, if it was 110 degrees with 5% relative humidity, it would actually feel cooler than it is. So the combination of heat index and wind chill, these are the real field temperatures that weather forecasters will tell you. So the temperature today, it's supposed to be 40 degrees, but the real feel is going to feel like 30 degrees. Or in Sacramento, it's going to be 100 degrees today, but with 50% relative humidity, it's going to feel like 118. So the higher the humidity, the less water evaporates off of our bodies. We cool ourselves not by sweating, but by the evaporation of sweat. So if the relative humidity is 100%, that means there's no energy to evaporate water. All the energy got used up making it feel hot. So if it was 80 degrees with 100% relative humidity, it would feel like 89 degrees. And you'll notice there are places that are off the chart. They are off the chart because it just doesn't. The heat index, the way it's calculated, I don't think it's valid for these temperatures. But just this summer, again, we saw 131 at Death Valley. I believe we saw 129 in Kuwait again at 50% relative humidity. And if you put those numbers in to get the real field temperature at the National Weather Service, 129 degrees Fahrenheit with 50% relative humidity, the real field temperature was 243 Fahrenheit. I don't think that's accurate, but it brings up an important scary point, and that is the hot and humid regions of the world are about to become literally uninhabitable. There are places in the world that the heat index temperature will be too hot for humans to survive for the first time ever in human history as a result of global warming. Heat waves. Australia a couple of years ago had to add new colors to their temperature maps because they had never experienced temperatures that high. That's a clue that you might have global warming if you keep having to add new high temperature colors to your weather maps. Climate change will bring more frequent heat waves. We know this. It's all happening. In fact, we can see it happening already. Climate change is here. Projections, or rather not projections, but from 1970 to 80, 80 to 90, 90 to 2000, the changes in average temperatures. Two patterns: the world is getting warmer, and the higher latitudes are warming faster than the tropics. And that's it for all of Chapter 2. That was fantastic. I hope you enjoyed that. Feel free to break that up as you need. Good luck with Chapter 2, and if you have any questions, please contact me.